Assembly language tutorials part 3. Here towards the end of the tutorial we will actually get to write some program. I know that it's been quite a theory, but we will see some program in this video. Let's get started. Assembly language fundamentals. These all slides will be available in GitHub. You could download it from here. I would put the link in the description section. Integers. What good is a program if it doesn't have some way to store data, right, and process something on that data, pass the input into that program and produce an output. If program is doing something on it itself, not communicating with the external world, what good is that program? So we start with integers. This is how you specify in your program that this is a decimal. You could have 10D as well, it means the same. This is binary. This is not 10, by the way. This is 1 0. This is octal, and so on. Here is a catch. If you have like hexadecimal literal beginning with a letter, like this guy over here, A10, so it should have a 0 if the hex value is starting with the A or any alphabet, which is A, B, C, D, E, and F in hex. So you should have a 0. So that's a quick catch there. Arithmetic operator precedence. Like normal mathematics, like how the mathematical equation we process, there is a order to that. I will not go into that. You are probably aware of that. It's not programming concept, it's normal maths. So you could check this slide and pause the video and check this slide. Real numbers, high precision mathematics, decimals. So we have something called IEEE 32-bit format, because the precision can be infinite, right? But we do not have that much space in the memory to have infinite precision. So what we do is we have 32-bit format, the IEEE. So I will show you how to convert a number, a kind of a floating point number, which is 12.375, which is a decimal, to convert it into this. How the hell this is such a big number? Because IEEE is this guy over here is a 32-bit format. So let's quickly go through that. How do we end up with this from this? This is the algorithm. What you do is you take the decimal part first, which is from 12.375, which is 12D. You convert that into binary, which is this guy over here. Take the fractional part, which is 0.375, multiply it by 2. This is how you multiply. So you would get 0.750. You keep the 0 somewhere and multiply 750 with 2 until there is only the fractional part left out is 0. So here you have 1, 1, and 0. And now 12.375 becomes this guy, which is got from here, and this guy, which is 0, 1, and 1. So this is how you convert some number, which is a fractional number, into binary. But that's not done. We are still a bit far away from IEEE 32-bit floating format. Now IEEE doesn't like this way. The floating point, the number is somewhere around here. It has to be like this, right? So if you move the decimal to 3 places, 1, 2, and 3, so what you end up is 2 to the power 3, right? It's a little 3 over there. So if I can increase the font, can you see that it's 2 to the power 3? So this is our number multiplied by 2 to the power 3, and these are all binary. So the exponent, now we have, because this is 8-bit sign, so we add it. In computer programming, if you want to subtract something from something, what you can do is you can do a 2's complement and then add that number to this guy. Instead of subtracting, you may add them. We'll not get into that. We'll deal with that later. So for 8-bit, what you do is you add 127 to 3, which is the exponent, and it becomes 130. Right? I hope this makes sense till this point. And what is the binary for 130, which is this guy? Okay. And finally we have three components: the exponent, the mantissa, and then the sign bit. So that comprises of 32-bit floating point format: 23-bit for mantissa, 8-bit which is the exponent, and we have 23-bit here. So now this part one, two, three, four, five, six, right? So here we have 1, 2, 3, 4, 5, 6. Now it has to be stored in 23 bits, and now these are MSB most significant bits. We store them from here: 1, 2, 3, 4, 5, 6, and make everything 0. And then the sign bit is 1. So we start with the sign bit because it's a positive number, so it is 0. Then 1, 2, 3, 4, 5, 6, which is the exponent over here, which is 1, 2, 3, 4, 5, 6, 7, 8. So you can count them exactly as is: 1, 2, 3, 4, 5, 6, 7, 8, right? And then it starts from here, and then this guy over here. So that's how you convert this freaking number into IEEE 32-bit floating point format. I know this is like ass backwards, but that's how the computation is done in the memory. Actually, that's the value which gets stored in the computer. Let's move on. Now next we have character literals, which are nothing but the alphabets, and then string literals, which is a kind of a stream of alphabets. We have identifier. How to define a variable? You use something called identifier. It could be a constant, it could be a function name as well. We'll in here in assembly we do not have function, we have something called procedure. It could be a procedure name as well. It could be a label. Suppose you want to mark a certain instruction in the code with some label, and you want to jump to that label, like a loop if you will. So you use identifier. We'll deal with these things later on. Directives is like C preprocessor, something similar to that but not exactly. So your program is broken into different sections, and you use different directives to specify each section of your program basically. Instructions, this is kind of the heart and soul of assembly program. Here is actually you specify those strings which we talked about in the first video, which would be converted by the assembler into binary. The instructions, like adding something to something. Assembling, linking, and running. The step is you have a source file, which is the assembly source file, and you compile, you assemble that. No question of compilation that exists in high level language. We have assembler. So that assembler will actually make that source into something called object code, right? It is not executable by itself. It's just your entire assembly source is converted to binary object code. In order to run in the CPU, it needs to be able to, we discussed in the first video that application. In the second video we talked about the application needs to communicate with the operating system. Operating system needs to communicate with the BIOS. The BIOS is the one which communicates with the hardware. So there is something in the operating system which can add something to the object code, the assemble object code from the assembly source file. Some ways, some other programs perhaps in the operating system which would allow it to sweep through the hardware and produce certain output, take certain input, and process something. There has to be external libraries. So that's the job of linker. There is something called linker which takes that object code of assembly program and links with the other operating system libraries or your own assembly programs, and then it produces the final product called the executable code. That's the one which actually gets executed in the CPU. That's the one. How does it happen? We have something called loader. So when you double click it or run the program from the command line, there is a utility inside the operating system called loader. It actually points the CPU's next instruction to the beginning of our program. So that's how our execution starts, and the loader's job is to do that much only, nothing more. After that, the application will execute by itself. Once it is loaded, it will execute by itself. So these are the components. I guess these slides are in different order. So source file, and then link, and then assembler, and then linker, and then loader. Then the program actually kicks in. There is a side note over here for your reference. You could go through that, pause the video. Defining data. These are like all the types of data that we can define. We have something called byte or signed byte. A byte is of 8-bit. We have word, D word, SD word, F word, Q word, T byte. This is interesting. We'll cover this in the next slide perhaps. Here are the high precision floating point numbers. We could even use dB for byte, dw for word, dd for d word, dq for quad word, q word, and dd for t byte. These guys are pretty old, so we used to program in this way like several years ago, like decades ago, but now we program like this, and even though we could use this as well, it's okay. Byte and friends. So I will not go through these slides. This is kind of a summary for the next 4-5 slides, so you could go through them on your own. So nothing but I am declaring some variables and stuff like that. Here I am declaring an array. You know, in assembly we do not have the concept of array. We have contiguous memory location, so that's an array. And here we have a matrix. A matrix can have s byte, byte, and s byte. It's possible, right? Because here we saw that s byte is also 8-bit and byte is also 8-bit. I hope it makes sense. We could have uninitialized declaration of the variables as well, using question mark, like this way. Same happens with word and friends. D word, SD word, stuff like that. Same story. These are for reference. This is the interesting part, which is called binary coded decimal packed BCD or T byte. It is 80-bit long container. It is mostly used for I will leave this exercise to figure for you to figure it out where it is used, but here is how it works. You have 10 bytes. The highest bit of the highest byte, like 10 bytes, the highest would be 1 byte, kind of the leftmost. So in that, what would be the highest bit? The leftmost bit. So that would be the sign bit, this guy over here. And then the lower 7 bits of the highest byte are not used. What we use is the remaining 9 bytes. So you have 10 bytes. Because BCD is 80-bit, so you have 10 bytes container, so you use only the 9 bytes to store the value. And there is something interesting in all of the 9 bytes, which is each byte can have, basically the definition of a byte is 8 bits. So each 4 bits or a nibble or a quad bit, I have not heard anyone using quad bit, but let's say 4 bits are called quad bits. So we can represent numbers from 0 to 9 using those 4 bits, right? So 1 byte can maximum hold 9. So if out of this 10 bytes, 1 byte is used for the sign, and remaining 9 bytes each can be split into like 4 bits each byte. So what you have is 9 cross 2, 18 places, right? 18 places. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So this is the maximum size of a BCD, and this is the minimum because of sign. And for the reader, I would encourage you to do this exercise, do this research, how BCD could be used for LED display. It's an interesting one. Real friends, it's like floating point. They are also the same as S word, D word, stuff like that. Little Indian versus Big Indian. It's simple, like this is the value. So if you want to store in Little Indian format, which is used in the Intel CPUs on the same CPU that we will be programming with, so least significant bit over here, least significant byte is 44, right? This is the most significant byte, 11. So least significant bit, little for least, big for most. So 44 would be stored first in the memory location, then so on. But in Big Indian, the most significant byte would be stored first, and so on. Symbolic constants. You define a constants in an assembly program, right? So these are not really constant, but kind of a placeholder for certain values. Like you see an example, move EX10. We will see some of these examples very quickly. I know that it's been a lot of theory, and I promise we would be having some code next 2-3 slides, and from there we would lift off and just coding only. No more slides, no more theory. Slides would be there, but less theory. So move EX10, no symbols. So if you could define something like this, temp equals 10, you could use move EX10. That's like symbolic constant, right? Kind of an example. So there are how it is useful. Like if you see here, if you could declare the value for pi, you could calculate the surface area of a cylinder. You do not have to use 3.14 everywhere, right? Continuation. So we have some interesting symbolic constant inbuilt in the assembler. So kind of a dollar is used for knowing the length. So if you have a temp equals hello world, if you have a byte over here, so if I could write something like temp byte like this way, so I could get the length like this byte. So it would work. It would give me the length of that. So now it is in the form of symbolic constants. We have something called EQU. Suppose you want it to be literally a constant. You do not want its value to be changed ever. So you declare it this way, EQU. By EQ 3.14, the value will never change. We have text EQU as well. Suppose you want to execute certain code chunks when you call something. So you could use text EQU. So suppose you have like this, add 10 to EAX, and you have placed the instruction inside this arrow brackets. I don't know how to pronounce it, I call it arrow brackets. You write it like this, so inside the code segment you could just invoke that text EQU, and this guy would exactly mean like this. Finally, it's time for some demo. Our demo here is a simple even odd program which I have pre-written. So here I'm checking like whether a certain number is even or not. So let's say it's not heck of a program, but it suffices the purpose. Num1 and num2 we have d word declaration here. One is 41 and 50. So there is a way to know whether it's even or odd. Kind of a tricky here. What you do is you move the num1 to EAX, because EAX is our extended accumulator register. This is our like general purpose register. So we always use EAX. And then symbolic constant. So if what is my div? My div is this guy over here, text EQU. We just learned that, right? So it would mean if I write this or write it like this, no difference, right? But there is an interesting part. Like inside that text EQU, I have another symbolic constant which is factor EQU2. How the hell this is working? Well, the assembler takes care of that. This is like how easy it is to write a program in this way. I could reuse it anywhere I want. So you would see the assembly instructions are always move EAX, EDX, push, call, stuff like that. But this is the beauty of writing the program in this way. You could reuse them, make it look like a C program or some scripting language. This is the power of macros. We'll talk about macros and procedures much later. It's not hard to program in assembly if you have these utilities. And by the way, MASM, this assembler MASM that we are using, it's kind of an industrial strength assembler. I really believe so. We could write any program here. So you call mydev, which is nothing but move ECX. Factor is EQU2. So move ECX 2. So now ECX has the value 2. Our program is to check whether it is even or odd. So how do we check that? We divide it by 2, right? So we have here, and this is the Intel instruction, the mnemonic div ECX. What it does is, after the division will be performed. Now EAX has num1 and ECX has 2. So EAX will be divided by ECX, right? So this is what you specify, even though it doesn't say that div EAX ECX, but it means that, right? The CPU understands that. So these are reference from the Intel manual, and you basically write it like this: div ECX, and it actually divides EAX by ECX, and the ECX will contain the result of the division, and EDX will actually contain the remainder. If the remainder is 0, we have our even. If the remainder is not 0, it's odd, right? So let's set a breakpoint over here and see it for ourselves. So num1 is 41, which is definitely it is odd. So let's see whether the remainder is 0 or not. So start debugging. It's loading the symbols. Now it is there. Now here is our EDX register. So our breakpoint is here. So I will step through it, step into. Now EDX is set to 1. It means that our num1 is odd, right? Let's test for num2, which is 50. So start debugging, build it, debug it. Now this is our ECX and EDX. Look closely, it didn't change, right? It stayed the same. So it means that our number is even, and sure enough num2 is 50. So you could test it like for any number. Like if I make it 40 and 51, so num2 should be odd. So let's test that. So the EDX value would be, this time it would be 1. So EDX, and I step through it, that code is executed, and sure enough EDX becomes 1. So now one more test, num1, which is 40. So it shouldn't change, and let's verify that. Step through, execute the next instruction, executed, EDX remains same, so it is even. So this is how you program, and it's a 32-bit assembly. I will show you one more demo, which is 64-bit assembly, which is over here. Nothing, just different registers. So here we have RDX, RAX, RCX, and everything is same. So if I place a breakpoint here and debug it, num2 loading the symbols. So many registers. I talked about that in the slide, that we have 8 more registers here. So here is our RDX. num2 is even, so it shouldn't change. RDX will not change, and sure enough it didn't change. So now let's have another value which is odd. Now num1 is 41, and by the way, this program is much simpler than before, even though it looks like, but you will realize eventually that writing program that way actually pays off. So we'll see that. So num1 is odd. Look for RDX value, and then here we have the change. So it's saying that it's not even. It's 41 is definitely not even. So I'll close off this, and I'll explain that what the hell was that program. Let's open that and dissect that piece by piece. So when you write a program, so how you do that, right? I will tell you how you do that, because it could be a little bit tricky. So you will have to use this link, and here I have 2 templates. This is 32-bit and this is 64-bit. So you just copy this entire thing, right? Just copy this entire thing Open Visual Studio. You have this Visual Studio 2017 Community Edition installed in your computer. Only then it will work. Open New Project. General Empty Project. Give any name you wish. And here is a directory wherever you want to specify. Hit OK. Should be empty project, like very clean. That's your project is ready. Project, build dependencies, build customization. Here we select this guy over here, Masm. Go to the properties. Properties, you have linker, system. You specify subsystem because these are our console programs. Even though later on we would be developing GUI application as well. And OK. Now you add a source. ASM, source.asm, and from here you can copy this template. This is 32-bit. I will show you how to assemble a 64-bit as well. You copy this. How these colors are coming, maybe in your Visual Studio it wouldn't come. So here we have extension and updates. So you go here and you search for ASM. You will get this. Install it, restart the Visual Studio, and you will have all these colors. So then you build it. Build succeeded. Our program doesn't have anything, it won't do anything. It's just nothing. So simple, exit 0, nothing else. So 32-bit program needs to be specified. If it is x86 architecture, mode is flat protected mode. Basically it will address values till 2 to the power 32 minus 1, which is quite a lot, like 4 GB something, which is a lot of RAM memory. Standard call means there are different calling convention, how you push parameters to the functions. When we talk about procedures in forthcoming videos, we'll talk more on that. Stack, you allocate a stack, basically a region in the memory. This is 496 bytes. You specify, these are like hash include stuff if you're programmed with C++, like specifying. Remember I told you the application needs to communicate with the operating system. The operating system needs to communicate with the BIOS. The BIOS actually communicates with the hardware. So here I was specifying some libraries, some programs inside the operating system like this. Like we have a program, so there are other programs inside operating system which are already linked, compiled, everything. It's just sitting there. We call them this way. Define the data section. Here is the code section. This is the main function, by the way. So here you define everything. Right now we don't have anything. So this is how you write your first 32-bit program. After that you could follow along my video and copy paste that program, clone it from GitHub, whatever pleases you, and you could run the demo. Now I will show you one more demo for running a 64-bit program. So I will copy this, new project, project 2, let's keep it there, create a new solution. Okay, same exercise, build customization, Masm. By the way, this process doesn't have to be in order. There is a good reason for that. Paste it, specify. Let's go to the linker, system, subsystem, advanced. Here you specify the main. So this is kind of a tricky one, so that's why I created the source first. Properties, macros, Microsoft macro assembler, it's set. Let's build it. I guess I have to specify the configuration as well. Configuration manager. Yeah, let's try one more time, and we are done. So I guess I'm doing some addition of something, so let's put a breakpoint here and let's see that. What the hell is that? So RAX, so RAX, whatever the value of RAX is 1. So after this instruction execute, RAX should become 6. So let's see that. Sure enough, it did. So these are the steps to compile a 64-bit program, to assemble a 64-bit program. We are talking about assembly, no compilation. It's a little tricky, a little different from 32-bit. I would say that start with 32, perfect your way around that, write programs, and there's not much difference between 32 and 64. So they are all the same. Once you know these things in and out, you would be amazed at what you could do. So I hope you guys enjoyed this video, and I will see you in the next video. Don't forget to like this video if you really like it, and for updates subscribe, right? It will motivate me as well, and I will keep making much more videos. And I hope you guys have a good day. Bye bye.